Particle interactions. The four forces. You will be familiar with the force of gravity. You'll also be familiar with electrostatic forces between charged objects, and magnetic forces between magnets and between electric currents and magnets. These two were found to be the same force, which became known as the electromagnetic force. There is also the strong force that acts between quarks and is responsible for holding the nucleus together, and finally the weak nuclear force, which is responsible for beta decay. All these forces come about through the exchange of particles. This animation shows how exchange of a particle can lead to repulsion between two objects. Here we have two ice skaters, and one of them throws a ball to the other. As the ball is thrown back, the first ice skater starts moving back due to conservation of momentum. When the second ice skater catches the ball, he also starts moving back due to conservation of momentum. So this was the exchange of a particle leading to repulsion. Now to look at how this occurs with the electromagnetic force involving two protons repelling each other by exchanging a virtual photon. Here we have the two protons. They're moving towards each other, exchange a virtual photon, and repel each other. This interaction can be represented on a Feynman diagram, named after Richard Feynman, who came up with this idea of representing interactions between particles. This is the diagram, and we have time going in this direction. So we have two protons, which at this point exchange a virtual photon between each other, causing them to repel. Here's our two skaters again, but this time the skater on the left has a boomerang. They're facing away from each other. The skater throws his boomerang, causing him to move backwards. The other one catches it, causing him to move backwards. So this has shown how an exchange of a particle can lead to attraction. And this could represent the attraction between a proton and an electron due to the electromagnetic force. The two exchange a virtual photon and move towards each other. This interaction can also be represented on a Feynman diagram. And here is the Feynman diagram, again with time in this direction. I haven't shown it on this, with the proton and the electron exchanging a virtual photon, causing them to be attracted. The lines don't show the actual positions of the particles. Now to look at some interactions involving the weak nuclear force. The exchange particles involved here are W+ and W- bosons. Others do exist, but these are the ones you need to be aware of. The weak nuclear force is responsible for beta- decay. This is where a neutron will become a proton, ejecting an electron or beta particle and an electron antineutrino. This is the Feynman diagram for beta- decay. Here's the neutron, which at this point ejects a W- boson, turning into a proton. The W- boson very quickly turns into a beta- or electron, and the electron antineutrino. The weak nuclear force is also responsible for beta+ decay. This is where a proton will become a neutron, ejecting a positron or positive electron and an electron neutrino. Here we have the Feynman diagram for this interaction. A proton at this point ejects a W+ boson, becoming a neutron. The W+ quickly decays into a beta+ particle or positron and an electron neutrino. The weak nuclear force is also responsible for electron capture. This is where a proton in the nucleus, generally a proton-rich nucleus, has a weak interaction with an inner electron, forming a neutron and a neutrino. So here we have the Feynman diagram for this. So a proton here and an electron here, exchange a W plus boson, the proton becoming a neutron and the electron becoming an electron neutrino. This has the effect of reducing the atomic number of the atom by 1 as it's lost a proton, but the atomic mass remains unchanged as this proton has become a neutron. This interaction can also occur when a high-energy electron and proton collide. A neutrino-antineutrino pair can be created from the excess energy. The electron, proton and antineutrino can form a neutron, ejecting the neutrino. This is the reverse of beta-minus decay. The exchange particles cannot be detected and still carry out their interaction, and so are called virtual particles. If they are detected in travel, the interaction no longer takes place. The more mass they have, the shorter their range. This table summarizes the main properties of the exchange particles for the four forces. You only need to know the electromagnetic and weak force in detail, but I've included all of them just for completeness. The exchange particle of the strong force are called gluons, and these are pi mesons. They have a range of around 10 to the minus 15 meters, a very short range. A relative strength of 1, that's what we're going to base the other ones on. And their effect, well, they hold the quarks and nucleons together against the electromagnetic repulsion in the nucleus. The exchange particle for the electromagnetic force is the photon. These have infinite range and relative strength of around 10 to the minus 2, 100 times smaller than the strength of gluons. Their effect is between charged particles. They are responsible for the attraction and repulsion between charged objects. The weak nuclear force has the exchange particles of W plus and W minus bosons. These have a range of only around 10 to the minus 18 meters, very short range, and a relative strength of 10 to the minus 6, much weaker than the gluons. The effect is beta decay, which is due to a change of quark flavor, and then the boson decays into a beta and a neutrino. And the exchange particle for gravity are gravitons, which have not yet been found. They have infinite range and a strength of around 10 to the minus 40, an incredibly weak force. Their effect is between objects with mass, and they're always attractive, which is why, despite their weakness, they have such a big effect on our life.